There are pneumatic transmission systems still mounted on building facades throughout Europe and North America that most pedestrians walk past without recognition. These installations consist of pipes, pressure regulators, and distribution manifolds riveted into 19th century masonry. They represent a complete alternative to electrical power distribution, and they functioned across major cities for decades. The hardware remains because removal costs exceeded the value of salvaged materials. The result is a fossilized infrastructure network that documents an engineering paradigm which vanished from technical education and public consciousness within a single generation. This is not speculative history. The systems are catalogued in municipal engineering records, described in thousands of pages of patent documentation, and physically present at verifiable addresses in cities including Paris, London, Birmingham, Munich, and Philadelphia. What disappeared was not the evidence, but the collective memory that these pipes once powered everything from textile looms to printing presses through pressurized air distribution networks operating at scales comparable to early electrical grids. The technical principle underlying pneumatic power transmission was straightforward. Central compressor stations generated pressurized air, typically at 75 to 90 pounds per square inch, which was distributed through cast iron mains to subscribers who operated pneumatic motors, tools, and machinery. The Paris compressed air system, established by the Compagnie Parisienne de l'air comprimé in 1881, constructed over 55 kilometers of mains, serving subscribers across multiple arrondissements by 1891. These were not experimental demonstration projects. Victor Pop's original Paris installation operated continuously from 1881 until 1994, documented in company records preserved at the Archives de Paris, and in technical specifications published in engineering journals including the Bulletin de la Société d'Encouragement pour l'Industrie Nationale. The system powered dentist drills, brewery operations, printing equipment, and thousands of industrial subscriptions, with pressure maintained through a network of 8 major compressor stations by the peak operational period during the 1890s. The engineering was not primitive improvisation, but sophisticated infrastructure requiring pressure regulation, moisture separation, main sizing calculations, and leak management protocols detailed in surviving operational manuals. If you want to support research that prioritizes archival documentation over simplified narratives about technological progress, subscribe to this channel. The conventional story treats electricity as the inevitable and superior choice for power distribution, but the pneumatic systems were not abandoned because they failed technically. They were displaced through a combination of economic factors, infrastructure compatibility advantages favoring electricity, and the rapid improvements in electric motor efficiency during the 1890s and the early 1900s. Understanding why one working system displaced another working system requires examining the actual engineering trade-offs rather than assuming teleological inevitability. The pneumatic networks functioned as designed. What changed was the competitive landscape and the economic calculation of efficiency losses versus installation flexibility. The Birmingham compressed air system, operated by the Birmingham and District Compressed Air Company beginning in 1891, installed mains throughout the industrial quarter, serving jewelry manufacturers, small tool shops, and metalworking operations. The system's specifications, documented in the Proceedings of the Institution of Mechanical Engineers, Volume 44 from 1893, describe a distribution network operating at 75 pounds per square inch with provision for higher pressure service at 150 pounds per square inch for specialized industrial subscribers. The company's prospectus, preserved in Birmingham Central Library archives, projected 500 horsepower of connected load by 1895 across subscribers in the jewelry quarter and gun quarter manufacturing districts. These were not niche applications. Pneumatic motors ranging from 1/4 horsepower to 50 horsepower powered metal stamping presses, buffing wheels, drilling machines, and the entire operational equipment complement of manufacturing facilities that would be considered mid-sized industrial operations today. The technical literature describes motor efficiencies, starting torque characteristics, and operational cost comparisons with steam power and gas engines. The engineering community understood these systems as legitimate infrastructure, requiring the same systematic analysis applied to any power distribution network. Physical evidence of the distribution infrastructure remains accessible at documented locations. The Paris system's main compressor station at Quai de la Rapée, constructed in 1891, stands as a preserved industrial monument with the original steam-driven compressor machinery maintained in operational condition for demonstration purposes. The building, designed by architect Henri de Glane, incorporated architectural features specific to housing large reciprocating compressors, including massive foundation structures to absorb vibration and tall ceilings to accommodate flywheel clearances. Walking through the facility reveals engineering decisions embedded in physical form: the placement of air receivers for pressure stabilization, the routing of distribution main-sized according to flow calculations, and the integration of condensate removal systems that address the moisture generated during air compression. These were not afterthoughts, but essential components of functioning infrastructure. Musée des Arts et Métiers in Paris maintains a collection of pneumatic motors and tools used in the system, including rotary vane motors, percussion drills, and hoisting equipment. Each item is catalogued with operating specifications and acquisition documentation that link it to specific Paris installations. London operated multiple compressed air systems serving different districts and applications during the late 19th and early 20th centuries. The London Hydraulic Power Company, despite its name, also operated pneumatic distribution in certain areas. Company records at the London Metropolitan Archives document this. More significantly, individual industrial facilities and building complexes installed localized pneumatic systems that remained in service for decades. The Michelin building on Fulham Road, constructed in 1911, incorporated a pneumatic tube system for internal communication and a compressed air distribution network for operating tire-changing equipment in the ground floor garage. Portions of the piping remained visible during building renovations completed in the 1980s. The technical specifications for these building-scale installations appeared in architectural and engineering references, including William Paul Gerhard's The American Practice of Plumbing and Steam, and Hot Water Heating from 1893, which dedicates substantial chapters to pneumatic power distribution in buildings, including pipe sizing tables, pressure loss calculations, and recommended installation practices. This was standardized engineering knowledge, not experimental practice. The patent record provides extensive documentation of the technical sophistication these systems achieved. United States Patent 239,180, issued to George Westinghouse in 1881, describes a comprehensive pneumatic power transmission system including pressure regulation, moisture removal, and distributed motor control. The patent drawings detail valve arrangements, governor mechanisms, and the integration of pressure accumulators for managing load variations. The technical depth of the patent application demonstrates that pneumatic power received serious engineering attention from leading technical figures, and that Westinghouse pursued pneumatic transmission before his extensive involvement in electrical systems. Similarly, Patent 252,491, issued to George Bailey Brayton in 1882, covers improvements in pneumatic motors specifically designed for distributed power applications, with claims covering rotary vane configurations, lubrication systems, and starting mechanisms. The patent literature from this period contains hundreds of related inventions addressing distribution networks, motor designs, pressure regulation, and system controls, representing substantial investment in developing pneumatic power as a mature technology rather than a transitional curiosity. The scale of installed capacity in major pneumatic systems reached levels that challenged simplified narratives about these being minor or experimental installations. By 1896, the Paris compressed air network had a connected load exceeding 18,000 horsepower, according to figures published in the Compagnie Parisienne's annual report for that year, preserved in the collection of the Bibliothèque Nationale de France. This represents more installed capacity than many early electrical utilities achieved in similar timeframes. The comparison is not between pneumatic power and modern electrical systems, but between pneumatic power and the electrical systems actually available in the 1880s and the 1890s, when electric motor technology was still developing. Electrical distribution standards had not been established, and the economic advantages of central station power generation were not yet proven. In that competitive environment, pneumatic transmission offered genuine advantages for certain applications: immediate, high starting torque without complex electrical controls, intrinsic explosion safety in environments handling flammable materials, simple speed control through valve regulation, and compatibility with existing mechanical power transmission knowledge. These advantages were not theoretical, but operational realities that determined system selection for specific industrial applications. The technical challenges of pneumatic transmission were well understood by contemporary engineers and documented in the professional literature. Compression generates heat, requiring intercooling in multi-stage compressors to maintain efficiency. Expansion causes cooling, potentially freezing moisture in distribution mains and requiring reheating at point of use for some applications. Transmission losses increase with distance more rapidly than in electrical systems due to pipe friction and leakage from mechanical joints. These limitations appear repeatedly in engineering analyses from the period, including detailed efficiency measurements comparing pneumatic transmission with electrical and mechanical alternatives. The 1895 article Compressed Air Transmission of Power in Cassier's magazine provides extensive loss calculations, showing round-trip efficiency of approximately 60 to 70% for pneumatic transmission versus 75 to 85% for electrical transmission over comparable distances using the electrical equipment available at that time. These numbers mattered economically, and the engineering community understood the trade-offs explicitly. The pneumatic systems operated despite these efficiency disadvantages because they offered other benefits that justified the cost in specific circumstances, particularly for industrial applications requiring high starting torque or operating in environments where electrical sparking presented explosion hazards. The transition from pneumatic to electrical power distribution was not instantaneous but occurred over decades as electrical equipment improved and installation costs decreased. The Paris compressed air system maintained substantial subscription through the 1920s, with major system modifications documented in 1927 when the Compagnie installed new turbo compressors to replace aging reciprocating machines. The Birmingham system operated until 1920, according to municipal records, and individual building pneumatic installations remained in service much longer. The factors driving the transition included improving electric motor efficiency, standardization of electrical supply voltages and frequencies, development of practical motor control equipment, and the greater flexibility of electrical wiring compared to pneumatic piping for reaching scattered load points within buildings. Economic analysis gradually shifted against pneumatic systems as electrical alternatives improved, but the technical capability of pneumatic transmission never failed. The infrastructure was displaced by superior alternatives rather than abandoned due to malfunction, representing normal technological succession rather than catastrophic failure or conspiracy-driven suppression. Understanding why substantial functioning infrastructure disappeared from collective memory reveals patterns in how technical knowledge persists or vanishes across generational transitions. The pneumatic transmission systems stopped being economically competitive and utilities stopped promoting them, while technical schools stopped teaching their design and operation. Within a single generation, the installed base aged out, maintenance expertise retired, and the physical infrastructure became archaeological artifacts rather than functioning technology. The process was not unique to pneumatic power, but it represents a general pattern where complete technical systems can vanish from active knowledge while physical evidence remains scattered through urban infrastructure. The pipes mounted on Parisian buildings, the preserved compressor stations, and the extensive patent literature document a technical capability that functioned at commercial scale for decades. What disappeared was not the capability, but the social infrastructure of knowledge, training, and economic incentives that sustained it. The lesson isn't about conspiracies or lost ancient wisdom, but about recognizing that technological change involves choosing between functioning alternatives based on economic and practical criteria that can shift over time. The pneumatic systems worked. Electrical systems worked better for most applications under the economic and technical conditions that emerged by the early 20th century. The displacement was rational but not inevitable, and the forgotten infrastructure remains as physical evidence that multiple technical solutions to power distribution existed as legitimate engineered alternatives during a period when the modern electrical grid was still emerging.